Grazie. Today we proceed with our convolutionary network for other type of problem, also very interesting, very universal problem. And the technology is so-called transformer technology. This is the theory of self-attention and theory of transformer. First of all, the theory, let us say two words about the self-attention theory. What is the self-attention theory? What is the attention, our attention? When we deal with some event and we interested in something in this event, so we should pay attention on some sector or some aspect of this event, yes? Our modeling situation will be automatic translation from one language to other language today. Before, we have taken only the model of type handwritten digit recognition, yes? Human handwritten recognition. And such a simple statement of the problem create a lot of techniques which consent us to enter in some good manner into the theory of neural net and in the theory of artificial intelligence. It is about the pattern recognition, but something like in image recognition. Other situation should be also very interesting, the speech recognition. The speech recognition is even more complicated problem than the image recognition. And there are a lot of techniques, but the neural net is always for excellence the theory which help us to make some auto recognizer of the speech of different humans. But today we shall consider the problem of automatic translator. First of all, the translator by Google. And really Google now adapted the technique of transformer also in the Google producing. Okay. So, what is self-attention? What is self-attention in the automatic traducing? Self-attention in automatic traducing is the following thing. When we have some sentence, for example, I am a student, and you need to translate it in francese. Per esempio, sì, je suis étudiant. Noi possiamo vedere, we can see that the order of the words are different in different languages, and the sense of the sentence is hardly dependent on the order of the words in this sentence. Yes, I am a student, je suis un étudiant, and so on. So we should to recognize the word, to recognize the phrase, and to construct the phrase in other language in the just order. If not just order, there is no sense. Yes, no grammatic sense. So we should grammatically correctly to construct the same phrase in other language. And what is the theory of auto-attention? Auto-attention. It means that, for example, you see, on the input of our some neural network, which has surely convolutional structure. Yes, it is typical convolutional network. I'm a student. I is the main word. Yes, I. It is personally. I am a student. So I is the main word. And the attention weights, you see, in some sense, we should make some calculation based on some data sets. Of course, you see, can be written digits, not on the zero, yes? You should use a big data set of American Institute of Statistics, yes? And there are 60,000 of training samples and 10,000 of verification samples. Also here in the language, we should make some vocabulary, some logical connection between the several words, and so on and so on. And we should take it in consideration, making the translation from one language to other language. So, what is the self-attention model? It is some structure of neural net for self-attention. And you see, I am a student. We have attention weight 0.5, M 0.3, a student 0.1 is 0.1. So we should make attention on the token, so-called token, the token I. We then represent the words as token. Token is the word or the sensible part of the word. So we have more important word and less important word, and we should define the importance of the words in the sentence, and then to begin from the most important, and then to take near the secondary word to complete the grammar correctness of the sentence. So it is typical example of putting the weights on the words which we should translate as weight of importance, and this procedure is called self-attention in the sense we are not who make attention to make the weight of attention of importance of the word, but the same system should choose correctly during the learning procedure the importance of certain words which we bring to the system for translating. Why is important the second model? It is translation, because translation it is some continuous process now. It is some continuous process. So it can model us. It can model us the procedure of statistical data elaboration, processing of our data of observation. For example, in astronomic field, yes, in astronomy you have a flow of some observation and measurements that you can get, and you can be sure that it should be some result of interaction between the material and the field of forces. Okay, is some result of interaction material, field of forces, and then after some distortion, the voyage in the space up to arrival to us, this signal, we should analyze this signal. And of course, there are a lot of external influences like powder spaces, like scattering, yes, like reflection, for example, like gravitation lengths, and so on and so on. We have some distortion, a lot of distortion, and we should anyway analyze it because it is the great natural laboratory of a lot of processes which give us a lot of information very useful. So you can imagine the continuing process of data processing as problem of automatical translating of the text. So the transformer architecture. Now let us affront the transformer architecture. So why is it transformer and so-called transformer? Because the aim is to increase the learning rate, and really it is 3 times faster than the usual Google translator used before. And now the Google adapted this new technology. By the way, the elaborated by the person who worked in the Google. Then transformers have much bigger performance than any other architecture of neural machine translation model, and then it is has high efficiency in terms of parallelization. So, as in the case of the convolute neural networks, where we have a lot of matrices with maps between them, so we can parallelize this process and have very effective and very fast result of training and calculation. And so how the transformer works. There is some input, like now phrases, je suis étudiant, then black box, the transformer, then we see what does it mean. And then the output should return us in English phrase, I am a student. So you can, and I spoke with the director of that you can make some catalog of events in the sense of signals of X-rays, arrivals of very interesting, not the cascades of photons, but single factor. And first of all, singlets be possible to register in some sense some entangled object interchange. It is very important because perhaps it is the most strong connection in the nature. So, do you know that if we have, for example, electron-positron Born, yes, electron pair, and one of these particles entry in the black hole, and the other go away. They have the joint sensibility. So the wave collapse of these two particles is immediately if one then other. So not possible to say that we cannot get any information from the black hole. It is not so, because there is an effect of entangled particles. That is why perhaps it is one of the most strongest direction between objects. Now let us detailize the work of the transformer architecture. So we have the input to some block which is named encoders. And encoders, what does it do? Encoders analyze this sequence of words from the point of view of some quantitative characteristics. There are three characteristics, three vectors, and three matrices, and three resulting matrices, transformation. And it can be considered as an ensemble of characteristics. So the encoders. Encoders is a stack, 1, 2, 3, 4, 5, yes, stack. So one cell, then go to the second cell, go to the third cell, and so on. A stack of encoders. Encoders is some functional part of neural net. Not important now what is its architecture, can be everything we tell about our objectives. And the decoding also, a stack of decoders in the same quantity as encoders, usually 6 or 8 coders and decoders, 6. The stack of decoders provided in the same number. Okay. So now more detailized is this architecture. So je suis en intelligent arrive to the first encoder, make some first elaboration with some hidden layer analysis, like in the case of convolutional neural net. Then arrive to other encoder, which have the absolutely same structure, but other weight and bias coefficient. And the same, the third encoder, the fourth, it's so on. So they test our phrase in let me say at different temperature, yes, analysis from the different quantitative characteristics. All encoders are identical the structure that I told. So each is divided by two sublayers, each encoder. There are two subblocks. Self-attention, first, self-attention. So this block, which elaborates some numerical characteristic in matrix form, and then feed forward neural network. Feed forward neural net, why? To characterize, and very important to have some output layer, which we can arrange, and it is very important, in which we can arrange for the specific activation function. I forget its name, but it is we have discussed. It is something like exponential in the XII summation A x A x A by K. The activation function non-sigmoid, but also has some sigmoidal form, and it is very important that it gives us the probabilistic distribution as output. So we have some coefficients which sum is equal to 1. Is the name of this activation function. Self-activation function should see the previous when we considered some activation function. Softmax function. Softmax function. So fit for self-attention to elaborate the characteristic of the words for any word which we have the enters. And then to normalize the output like some probabilistic distribution sequence. The exact same network is applied independent for each word in the sentence. So we have the enter of several words. There are some entering, so we can elaborate for the word. Very interesting thing that for the traditional even neural net translator, yes, we have degrade of the quality of traduction, yes, translation, with the increase of the number of words in the sentence. And if we have, for example, 2 pages of some detective story, we have big degradation of the. We should use only with its short phrases. But using this architecture, we have absolutely no problem with the degradation of the quality of translation. Absolutely. So we have possibility to continuously analyze the flow which arrive to us. It's for scientific from the scientific necessity is very important. We can observe, for example, some astronomical data. We can observe some biological measurements. We can observe some electronic microscopic object and have some analysis. So we should not to limit some short sequences. So encoder is self-attention feed-forward, but the decoder is consists of self-attention also, then encoder-decoder attention, and then feed-forward. Why encoder-decoder attention? Because we change the order of the words according to grammar rules. So we need to take into account the difference between languages for correct grammar, correcting construction of the phrases. So what is the work of encoder and decoder? It is transformation by word embedding algorithm, word to vector. So now we formalize in some sense, we formalize the word. Okay? We formalize the words and we represent the words as vectors. For example, je suis étudiant, 3 vectors. Absolutely important that they have the same dimensionality. So the dimensionality of our entering and output words should have the same dimensionality. And here in this algorithm, the variable dimensionality can confuse all our procedure of correct translation and correct training and so on. So we should limit absolutely to choose some good dimensionality and to put it into these boxes. And each word is converted into a vector of the length 512. Why 512? What is 512? It is 2 to 9. 2. So 8 to the power 8 is 1 byte. 2 minutes. Okay, so it is 4 hexing hex symbols. Yes, nibbles. 2 nibbles. One nibble is 4 bit. For example, 0, 0, 0, 1, and so on, and the maximum FF. It is 2.8. So the ASCII code is 7. Okay. The ASCII extended code with some control symbolics is 2.8. So 8 bits. But since we can have some numbers, 1 bit should reserve for the sign, plus or minus. So that is why 9. So what is the codification of this XII étudiant? We can see a ASCII table, and we can compile these boxes, and in this sense we can formalize as vectors, yes, which is called embeddings. It is technical terminology. It is embedding, and the word, if the word longer can have longer than the 512 bits, what should we do? We should truncate this word and consider the token. The token is a part of the word. Of course, the token is not the best invention because, for example, we can codify some word universe, but it can mean universal, university, or universal or universe, for example. Three different, but it is small problem. Small problem. We don't bother about. So each word follows its own path in the encoder. So je suis again, then self-attention, they produce some result, Z1, Z2, Z3. What is this result? We shall see this. Okay. The encoding in detail. Encoder 1. Now let us simplify the phrase. Not je suis étudiant, so that we consider only thinking machine. Thinking machines. Two words. Thinking machines. So X1, X2, self-attention. Then the self-attention should give us the coefficient of importance of these words, and to make like output Z1, Z2, two vectors of the same dimensionality. It is especially for vectors of the vectors, and then to pass feed forward neural net and to elaborate new numerical vectors R1 and R2, and then to bring to the encoder 2, and so on. And there are 6 encoders. So the mechanism of self-attention, what is it? How it works? The input sentence, we want to translate. The animal didn't cross the street because it was too tired. What does it refer to this in this sentence? So we should consider some correspondence with it to all other words, and to evaluate the importance of connection between it, for example, it was animal, or it street, or it what. In this situation, animal. In other situation can be street. In other situation can be other. But self-attention should characterize it itself correctly. When the model processes the word it, the internal attention, this layer, helps to understand that it refers to animal. Okay. As the model processes each word, each position in the input sequence, internal attention allows the model to look at other positions in the input sequence and find a clue, yes, a hint to better encode that word. Encode in the sense of make some numerical characterization vector for it to pass to other layers. And on the decoder, we should assemble the other phrase in other language. So we should have some characterization. The self-attention mechanism is a technique that the transformer uses to simulate understanding of other relevant words when processing a particular word. So we have the phrases for this such division of token, but it is specific for some specific network. So the animal didn't cross the street because it was too tired. And then it begin to see the animal didn't cross and so on. And we can see, for example, the grade of dark of this window, like the reflection of the value of the coefficient of importance. So, how to compute the self-attention? It should compute some numerical characterization of the word which entered in our analyzer, yes, in our neural net. So first step is the following. Create 3 vectors from each input vector. In our case the embedding is of dimension 512 of each word. Yes. Then to elaborate 3 object vector. Query vector of dimension of 64. Key vector also dimension 64. And value vector also of dimension 64. This dimensionality is not very, very important. It is only for several combination of several languages. European type, it is optimal. But for example, some Chinese and European language should optimize other quantity, but it is not important for us. So we can take it as it's indicated. So inputs, our inputs, thinking machines should be packaged in some embedding codification vectors. Yes, now this vector of the fixed dimensionality of 512. 512. Then to elaborate of other shortly queries. Queries is really query. So we see our main word, and then to query which word in which order of importance are related to this main word. Yes, for example, it. So it is query. Keys, yes. Keys query is we take our main word and begin to query on each word. Then key is each word which we have in the query. And values. It is a value of importance for any our query. And so we have embedding x1 for the word thinking and x2 machines. Yes, we have only two words, these short phrases, two queries, two keys, two values. And we have also three matrices of weights. Three matrices of weights, which we should have trained during our training procedures. So we can start our matrix WQ, so weight of query, weight of key, a weight of values also. So we should attribute some values to the vectors, keys, values, queries for 1, 2, 3, for 1 and 2. Multiplying x1 by the way, for example, matrix WQ produces Q1, the query vector associated with this word. And WQ is firstly is a matrix of random numbers. Usually we use random numbers which has Gaussian normal distribution with parameters, the middle value, yes, the average 0 and the dispersion 1, the square, mean square ratio. As a result, we create query, key, and value projections for each word in the input sentence. Okay? So by multiplying x1, x2 by weight matrix WQ, for example, Q1, WV, V1, W, what is K, K1, and so on. Second step, getting the coefficient score. We should now to make some score, like examination, yes, examination mark, score to the importance of our work. So we should evaluate the importance like a score. It determines how much to focus to other part of the incoming sentence while encoding the word in the particular position. So, taking a word in particular position, for example, it, yes, we make some estimation, yes, our score, premiums, to all the words, which reflects the grade of importance for the word in a certain position. The score in the position 1, number 1, will be the scalar product Q1, K1. The score in the position 2 will be the scalar product Q1, Q1, K2. So now we can resume it like input, thinking machines, thinking the score. You see, we have calculated, and now score thinking 112 and the machines now 96. So step. Now divided the scores by 8. The square root of the dimension of the key vectors used here is 64. What does it mean? What does it mean? You see, usually we firstly, before our training procedure, we compile our numerical arrays by random numbers, which have normal distribution, with the middle value 0 and the square deviation 1. Okay, but then we should take this course for the next steps and to add these characteristics. So it is like we have the summation of random variables and random variables Gaussian independent random variables with 0, 1 characteristics. What does it mean? The mathematical expectation of sum is the sum of mathematical expectation. Sum of zeros is 0. But the summation of mean square deviation should be added. Should be equal to n. And this can present us very big problem, because when we increase the mean square deviation, we increase what we increase. We increase some big noise in our data. Yes, the square we can. And during our iterative procedure, we can accumulate big error of the noise, of random noise. So in order to evitate this, we summarize these numbers and the quantity of 64, and divide by the square root of 64.8 at any step. And we still have the characteristic of new Gaussian process, like the summation. It is also Gaussian process. We will have deviation 1 and mean value 0. So we have not more the influence of increase of noise. Fourth step. And then pass the result through the softmax function. This function. Yes. And a very beautiful thing that we shall have the probabilistic distribution softmax with 0.88. You see, score will 112 and 96 should be very, very near. But softmax division, yes, the probability give us that the softmax importance is 0.88 and here 0.12. The result in softmax score determines in which measure each of the words of the sets will be expressed in the certain position. So, of course, we should express the position in the phrase, because the sense, the grammatical sense, is very important. The fifth step is multiply each value vector by the softmax factor before adding them. The point is to take irrelevant work to the background, but by multiply them by small values, for example, 1/10,000. 1/10,000. Six steps. So we truncate now the words of small relevance. We have some other truncation in the procedure of this transformer architecture. So six step, add the weighted value vectors. This will represent the output of the layer of internal attention in this position for the first block. So we have thinking machines, input, embedding some x1, x2, queries. We elaborate then some numerical vectors, yes, queries, keys, and values by dimensionality of 64. Then, as usual, score, divide, then normalize, softmax apply. And then softmax V1, we have the value sum V1, V2, and the summation, it is Z1 and Z2. This completes the calculation of internal attention. As a result, we get a vector that we can pass to the feed-forward neural network, then to have some progressive distribution, then in order to pass to the next encoding or decoding module. So now we have seen it like some vectorial calculation, but now let us take it together as matrix calculation. Matrix calculation is very good because it can parallelize our calculation. So we have X multiplied by weight matrix WQ, and to have some matrix Q. Also X by weights WK, and have the query, then keys and values. But now we can do it in matrix form. So each row in the X matrix corresponds to a word in the input sentence. We again see the difference in the size of the embedding. 520 we denote like 4 squares in the figure, and query key at value vectors 64 or 3. We have defined this in such a mode. So 4 squares is 512, and 3 squares is 465. The general formula for calculating the output of the self-attention layer is the following. Softmax applied to the multiplication of Q, yes, query per key transposed divided by square root of dk, yes, 8, and pointwise, yes, pointwise, but multiplied by v, it is our element-wise multiplication is. The multiplication of range name this operation. This French mathematician is the name of French mathematician. Recently read. There is also some quantistic operation in quantum calculus. The node is the main operation, and the transform later. I will remember. So this is the operation of multiplication, element-wise multiplication matrices, and we have the resulting matrix Z. But it is not all. Now we announce that one attention is not enough. They use also multi-hit attention. So we replicate this attention. The same structure, but other coefficients. So the attention layer is provided with many representation subspaces. So apart the fixing of some connecting of some place in the phrase of some word, they consider several representation subspaces, and in order to use the variance of different position of this word in function of some sentences and its grammatically significance. So we see it is so-called multiple attention, and of course we have such the replication of, for example, 8 times the same thing. It can be done, and we have 8 different representation subspaces. So the transformer uses 8 attentional hits. So we end up with 8 sets for each encoder decoder. Each of these sets is randomly generated. So we randomly generate 8 times. It is experimentally it was found that it is some near to optimal quantity of replication of our experiments. Further, after training, each set is used to display incoming embeddings. So for each independent set of observation, we have different matrices, vectors, yes, and grade of importance. For example, attention hit number 0, and our normal procedure for this. The matrices query, key, and value. With the corresponding weight matrices W0, Q, W0K. The same for index 1, the same for index 2, and so on. Beginning from 0 for 8, we should finish to 7. So we have a set of different matrices and values. And it is a challenge. So we have now thinking machines and calculate 8 different random chosen attention blocks. But the feed-forward network layer does not expect 8 matrices to arrive. It waits for only one, a vector for each word. Okay? But what we can do? We can append this matrix, yes, concatenate this matrix for attention hits when we calculate Z of 0 and so on, Z7. Then we can train a big matrix W0. Yes, it is a weight matrix. And then the result would be Z matrix that captures information for all the attention hits. So we can set this forward to the forward feed neural network. So we can append, we can summarize. Sometimes not append, not concatenate, but summarize. One can do some arithmetic medium values element-wise, element-wise of all my matrix, and so on. A lot of compression of this information. In this situation, we train a big weight matrix and we multiply by weight matrix and have a compact matrix as for one hit attention. So then, representing order in a sequence using positional encoding, and this is the problem. The positioning of the word is important. So, and we should add some position the phrase of every word. So in embeddings, we should add some information about its position. Unfortunately, today I have not enough time to explain very interesting thing that we can calculate 1, 2, 3, and so on position of the word by a couple of sinus and cosinus of some arguments plus phase, shift phase. And this shift phase is very beautiful thing. This shift phase means that we can define linearly the number of the integer number of position the word. It is very beautiful thing because there are the formulas of cosinus x plus omega, something like this, and then the same thing, same thing. This vector, which is its norm? Pythagorean theorem, the summation of quadratic. 1, very beautiful. Then we have some formulas of such cosinus x plus y is equal to, you can see what is it, and sinus. And it gives us excellent instrument for calculation of integer number of the position of the word in the trace. So the positional encoding also can be marked in the color from yellow to blue, from -1 blue 4 to +1 yellow here. And one can also codify it and make some typical template of positioning, like this. In the scale of blue and yellow, and we have some discontinuity in the middle of this illustration, because the left part we use for cosine, and the right part, with other argument, we made by sine. And you see, there's 512, and here we have 12 values. The encoder typical structure is the following. So, thinking machines, the trace of two elementary words, only two thinking machines. So, plus positional encoding by sine and cosine. We pass through self-attention. Then it is an encoder. Add and normalize. Then feed forward two words. And then also add and normalize. This is typical encoder number 1. And we have 6 encoders. More in detail will be self-attention. Yes, we have XI plus positioning. There is this is additional information. Self-attention. Then the exit is Z1, Z2. Then layer norm. We have the summation of X plus Z. And we bring here the information about the positioning. Then we elaborate Z1, Z2 like the output. It is other vectors, with other coefficients. Then feed forward layer, neural net. Yes, for the last layer to normalize for normalization. I told you what is the name. Softmax. Okay. In the typical transformer, like two stacks of stacks of encoders and decoders. Stakes nel senso, diciamo, di anello chiuso, diciamo, e abbiamo le corsie, diciamo, di calcolo, diciamo, su questo senso, diciamo, stacks. So we have thinking machine, then self-attention, add and normalize, feed forward, add and normalize, set, and so on. Here only 2 decoders, and then encoder, which look the difference between languages of sequence in the trace. So we have the analog in the other language, but important to make in the just position. So and the same thing. Linear software at the exit should be our translating. So I think I finish today without big details. Very beautiful cosine and sine modification of position. It is very interesting because it is not linear functions, but they represent by their construction and the phase shift the integral position is very strange thing. So it is. And again, I would like that for astronomic, for example, for astronomic observation, it can be very interesting thing because we can express like some words. Which words? Words of some photons expressed in the longness of wave, yes, lambda. The tempistic of Ariel, the polarity. You can apply a filter, polarization filter. You can shift the polarity. You can do everything. You can elaborate this language of some signal to detect something. And such structure can give some hints. Of course, everything to construct ex novo, but something can be very interesting. So now, if we have not more, if you have not more questions, let us finish. Unfortunately, I have only 32 minutes registration.
I think it's
It is normally
we have no cover.
blockado.